This is EE597 with Professor Krishnamachari on Wednesday, May 25th, 2016.
Can I have the overhead camera, please? So let's start again with a recap. We've been talking about the file layer. So last week, I guess, on our first class, we started talking about digital communications. Specifically modulation schemes and their performance under additive wide Gaussian noise. And then on Monday, we started talking about radio propagation. And we started talking about radio propagation modeling. Specifically, the model we're starting out looking at is called the simple path loss model. And then with log normal fading. I think I also mentioned briefly a different model which has some dynamics in it, which is a Markov chain model. And then we also talked about performance of modulation schemes under fading. So just to reinforce what we talked about, we said that whatever modulation scheme you have under AWGN, you can always describe the bit error rate as some function of the SNR. And in a fading channel, the SNR or gamma is a random variable with some PDF, let's call it G of gamma. I want to be consistent with my notation. I think that's what I called it last time. Is that right? I called the distribution G. Okay. And so the idea is that the probability of bit error is a function of something. If it was deterministic, like an AWGN, the SNR doesn't change. You have a certain receive power, you have a certain noise that gives you the SNR. So this deterministic function is the probability of bit error. So this itself would be just a constant. If you fix gamma, this would be a constant, or if I vary gamma, it's this function. It's monotonic. And so all we say about it is it's some monotonically decreasing. Because the higher the SNR, the smaller the bit error rate would be, right? So this distribution, which we call a fading distribution, is something that characterizes the radio environment. This function is a function that characterizes the radio itself, the modulation scheme you're using. So this is somehow and the fading distribution characterizes the environment. So you can expect G of gamma to look different depending on your physical location. You know, whether you're in a building, what type of building it is, which room you're in. If you're outdoors, what the outdoor environment looks like, how many things are nearby, how reflective surfaces are there objects in the way, are there dynamics in the environment, are the nodes moving, all of those things will show up in this distribution. Okay. So ultimately, when you talk about performance of communications for wireless channels, it's a combination of what radio you're using and what environment you're operating in. Right? Whereas for traditional point-to-point links, there's no varying the environment. They're fixed. Wherever they are, that's where they are. You just measure the receive power. It's not going to change. Right? But in a wireless environment, this is something that's always dynamic, uncertain, captured by distribution. So we said there are two approaches to characterizing performance. Approach one is to compute the expected probability of bit error. And this, we said, is simply integrating your function over that distribution that you have. Okay. So this is what we call the expected or average bit error rate, where the averaging is averaging over the environment, all the stochastics of the environment. Okay, sometimes we denote this gamma here to say it's an expectation over the gamma, which is the random variable. So at the level of abstraction that this, how I'm recapping it here, it doesn't really matter what the G distribution is. It can be any distribution. Whatever it is, it's describing what my environment looks like. And as you can imagine, it's different for different environments. How do we figure out what that G is? Right? That's how do we model the real world. Okay, so that's the job of statistics. So there's a difference between probability and statistics. Probability starts with you're given this distribution, what can you compute about it? What is the CDF? What is the expectation? Things like that. But there's statistics which says you have a real world data set from which we want to infer what is the distribution, what is the mean value, what is the variance, things that we want to learn, basically the model that is best representing what the real world looks like. Okay. And so some statistical analysis of the environment is needed to generate this function G. Okay, just empirically you have some way of generating it. Sometimes you use existing models that people have studied in the past. So log normal model is an example of a model people have studied well in the past and seems to fit many environments. So you just use that model, but then you still have to figure out parameters. So if you remember the log normal fading model, there are parameters. The fading itself has a parameter of the variance. Okay, and so how would you figure out the variance? You'd have to measure in that given environment what the variance was. And in the next homework assignment, you'll spend some time figuring out the distribution at a given distance based on real data. So this approach just says I can characterize my performance if I know the SNR distribution and I know how my bit error rate is as a function of the SNR. Approach 2 says maybe I don't care about the actual bit error rate, but I've already what I care about is some threshold on the bit error rate. I don't care what the exact value is. I just want to make sure it's below some number, right? And this number is you're starting with a threshold. So start with sort of a bit error rate threshold. Let's call that PB threshold, right? And you don't want your bit error rate to be below this. So if you start with this threshold and you insist that your such that want the probability of bit error rate to be always less than PB threshold, then given this function f of gamma can derive an SNR threshold. Let's call it what did we call it last time? Theta. Did anybody remind me what? SNR or outage? Yeah, we call it outage, right? So some threshold called theta out, such that such that we want the gamma to be always above this theta outage. Okay. And so long as this condition is met, that the actual SNR is above this threshold, then your probability of bit error will be less than the threshold bit error probability. And what number that should be will come from your application. So depending on what you can tolerate for your link, maybe you can tolerate one error every 1,000 bits, maybe you can tolerate one error only every 10,000 bits, 100,000 bits, whatever that is. You start with that number, and then since this is a known function, you can figure out what is the corresponding threshold, right? This is just a monotonic function, so there's a mapping between every bit error rate and a SNR value. So you start with this outage probability, and then you just say, what is the probability that your link is an outage? So what we called, I think, P outage is the probability that your gamma is ever falling below this outage probability. Okay. And this would just be the integral from negative infinity to the outage threshold of your fading distribution. Okay. And the second approach of computing an outage probability is different in that it's not giving you the average error rate at that point. It's just saying that if my application is satisfied with a certain bit error rate, this is how often I am unable to achieve that. Notice that both of these are sort of errors, so you want this probability to be low, and similarly you want this outage probability to be low, right? This outage probability to be low. So we always want these two different metrics to be as low as possible, but what can we do to control the link? So if we want a lower bit error rate on average or a lower outage probability, what can we do as engineers? Increase the signal power. That's one thing that's always under our control. We could change the modulation scheme. Intuitively, would you use a higher or lower modulation scheme if you want to improve these lower? Okay. And we've talked about this before, that there is this power throughput error rate trade-off. So basically, we can either increase the power or reduce the throughput if we want to control the error rate. That's really what we have under our control. So, okay, so we kind of have already a basic understanding. We know how to model what the channels look like. We know how to model what we're communicating over the channels, and we know how to describe the performance. This first round of looking at all of those was like a somewhat simple view of a wireless channel. You can go a little bit deeper into understanding how fading happens. And so let me try and dig a little bit deeper into that. Okay. So it turns out that there's a little bit more subtlety to how fading happens and what the challenges and opportunities are that it presents. One issue with fading is an issue of these multipath reflections causing delay in the signal as it arrives. Okay, so this is called the delay spread problem. Due to multipath some of the reflections arrive late. And this turns out to be a problem when you're trying to send data at a very high throughput. So if you want to send megabits per second, tens or hundreds of megabits per second, what can happen is that while you're sending the next bit, there are reflected versions of that first bit that are still working their way through the environment and reaching the receiver. Okay, and what this causes is something that's known as intersymbol interference. And we actually have experience with delay spread sometimes in these echoey environments, or even if sometimes you're on a really bad phone link and you're hearing echoes on the line. First of all, it's really annoying. You're trying to speak and then you're hearing sort of echoed versions of what you're saying or what the other person is saying. But if you're forced to live with it, you can't really change that line or call again. Or if you're in an environment, you're in a cave, you have to talk, there are these echoes. Typically, the response that people have to deal with it is they just start speaking slower. You just say one word, wait for all the reflections to clear off, say the next word, wait for all the reflections to clear off, say the third word, and so on. So in some sense, the challenge here is that because of the echoing effect, putting together your symbols at a very high rate causes them to smear into each other, makes it hard to decode what they are. And so if you have a way to kind of spread out your symbols, slow things down, then you can deal with it. Right? That's sort of the problem of delay spread. The other thing that sometimes happens with respect to fading is called Doppler spread. And this is due to mobility of the sender or receiver or even objects in the environment. The carrier frequency gets shifted up or down. And that effect you might have seen in high school or college physics is called the Doppler shift. So if you have a source that's emitting a sine wave and it's moving towards you, because the wavefront, so the source itself is moving closer to you, the crests of the wave start appearing quicker, and so it's as if you're now experiencing a sinusoid with a higher frequency, right? So you slowly see an increase in the frequency in that case. In the other direction, if you have a source that's moving away from you, you'll see that the crests are starting to come slower and slower because the source itself is moving, and that's as if the carrier frequency has been shifted down. So if you have a wireless channel in which the source keeps moving, the destination keeps moving, or there are even objects in the environment that the signals are reflecting off of, and those are moving, and there's a lot of dynamics there, then you're going to see that the carrier frequency is getting modified. Okay. So these two phenomena, one of them is kind of a temporal spread of the signal. The other one is like a frequency spread of the signal. And from a receiver's perspective, they can both cause problems. So on the Doppler spread front, what can happen is that because your kind of carrier frequency is changing, you're going to start to see some distortions in your signal. And also, you'll find that as the carrier frequency changes, there are times when the signal looks really good and times when it looks really bad. This time-varying phenomena of the fading, how quickly it changes, is a function of the Doppler spread. Okay. And so, kind of, if I were to kind of think of these things in the time and frequency domain, Doppler spread is measured as some quantity in the time domain. You talk about how many nanoseconds or microseconds or milliseconds the Doppler spread is. So this is measured in units of time. Sorry, not Doppler spread, delay spread. And on the frequency side, you have this thing that you measure, which is the Doppler spread. So it's called this Fs. It's called this Ts. It turns out that there is an equivalent metric in the other domain for each of these. So delay spread is connected to something known as coherence frequency or coherence bandwidth. And I'm going to call this, what shall we call it, like W coherence. And the Doppler spread is associated with a phenomenon in the time domain that's called the coherence time. One way to think about why this might be happening is as you're, take a very simple example, you have a source and a destination, and let's say there's just a single multipath reflection between the source and the destination. Let's say that the destination and the source are static, but something in the environment, this object that they're reflecting off of, is moving. Then as this object moves, the other effect that's going to happen is that the multipath phase keeps changing, right? Because your phase shift keeps changing because you're traveling different distances. And as that keeps changing, not only are you seeing the effect that has to do with sort of the frequency domain, but even in the time domain, the phase shifts as they keep changing the reflected signal sometimes will be constructively adding and sometimes will be destructively adding. And as you can imagine, the faster this object moves, the quicker those amplitude changes will be observed. And the same thing will happen if the receiver is moving as well. Like even if the receiver is moving, the objects in the environment were not moving, all of these different components will add together, and how fast they fade in and out of being a strong signal to a weak signal will be a function of the speed. Okay? So this movement not only affects the spread in frequency, it also affects how long does it take for a channel to go from being good to bad or from bad to good. Okay? So this is described as coherence time. Let's call it T coherence. And roughly speaking, these are inverses of each other. So the coherence time is inversely proportional to the Doppler spread. And the Doppler spread itself is kind of proportional to the velocity of the relative velocity of the vehicles or of objects in the environment. So how fast things are moving in the environment are going to affect the coherence time. If you have an environment where nothing is changing, your source is static, the destination is static, the objects in the environment are not changing, then the relative velocity is zero. There is no Doppler spread effect that's happening. The coherence time effectively is infinitely large. Whatever the channel condition is, it stays that value forever. Okay. And if you have a lot of dynamics in your environment, even if your nodes are static, but there are people moving around, the reflections are moving around, your Doppler spread is going to be high, and correspondingly the coherence time is going to be low. Your channels are going to go from being good to bad very quickly. Okay. So coherence time is related to something we call how fast the fading is. So if T coherence is low due to dynamics of nodes or objects in the environment. When I say objects in the environment, I guess I really mean kind of scattering and reflecting objects in the environment, right? Scattering or reflecting objects in the environment. And humans turn out to be, in the RF spectrum, actually cause a lot of variation in the radio signals. So if you have people in a room and you have a link where the source and the destination are just static, but the people are moving around in that room, that's going to cause an impact on the fluctuation of the signal. Many of you have experienced this sometimes in more traditional radios. Sometimes you just stand close to a radio and you suddenly start hearing a certain buzz and you move away and it doesn't seem to. It seems like your presence is affecting the radio signal, and it really does, because we're basically bags of water, and water resonates at the frequencies corresponding to RF signals. It absorbs RF signals and reflects RF signals. So if it is low due to these dynamics, then we say the environment is experiencing if frequency is low, we say it's experiencing fast fading, right? Else, we call it slow fading. On the other hand, if you look at the delay spread, I think I call it TS, this is proportional to 1 over the coherence bandwidth. And if the coherence bandwidth is small, i.e. TS, the delay spread, is large, we say the environment shows frequency selective fading. Else, if the coherence bandwidth is large, then we say we have something called flat fading. So these phrases, fast fading, slow fading, flat fading, and frequency selective fading show up sometimes in the literature when you're describing what the channel is like. If the delay spread is large, that's when we have problems with intersymbol interference. So frequency selective fading is when we have intersymbol interference. There is a physical meaning of the coherence bandwidth. It means that if you were to change the carrier frequency by a little bit, how different would your attenuation look? It turns out that when you have channels with large delay spreads or small coherence bandwidths, changing the carrier frequency a little bit can dramatically change the attenuation of the signal. Okay, so just changing your frequency by a little bit can make that link look better or worse. If you have channels in which the delay spread is small, which means the coherence bandwidth is large, then sort of the channel response is not that sensitive to what the carrier frequency is. Okay, so I won't get into the physics behind that, but basically if you think of the channel response in both the time and frequency domain, you can kind of show that the delay spread has some implication with respect to the carrier frequency of the signal. So sometimes the frequency selective and flat fading issues are harder to grasp intuitively, but the slow fading and fast fading is very easy to grasp. It's basically, slow fading happens when there's nothing moving in the environment. Whatever the links are, they stay at that value. But in a fast fading environment, they're changing dramatically. So last time we talked about creating a Markov chain model of the environment. If you create a Markov chain model of the environment in which those SNR values over time are fluctuating a lot, that would be a fast fading model. If you have a Markov chain model in which whatever state you're in, you tend to stay in for a long time because maybe there's self loops into the same state with very high probability, then that's like a slow fading version of the model. I'll talk about that a little bit more in a bit. with respect to coherence bandwidth, for now, and for our purposes in this class, it's enough to realize that, again, it's a function of the environment. For certain environments, the coherence bandwidth is small, sometimes it's large, or the delay spread is small or it's large. If you're in environments where the delay spread is large, the biggest problem is that it's basically a very echoey environment for RF. In such environments where there's a lot of reflective surfaces, your multipath signals, the reflections are showing up many, many units of time. Typically, these are all in nanoseconds or hundreds of nanoseconds later than the original signal, which causes them to, or even sometimes on the order of a microsecond, start smudging into the next symbol. Okay, and we experience this as a problem when we're trying to send our symbols very fast. So really, this issue is something that only shows up when you're talking about high data rate communications. So we typically don't worry about whether the channel is flat or frequency fading if we're working, for example, with low power, low data rate wireless networks. We typically worry about these in more high data rate settings. Right? So in cellular communications where you're trying to send data in hundreds of, tens to hundreds of megabits per second, and for 5G they want to get it to several gigabits per second, these issues are really important. And we'll talk about a couple of techniques that have been developed to deal with the delay spread issue. One is to reduce the possibility of intersymbol interference by splitting your stream of data into a bunch of different low-rate streams. And that's a technique called OFDM. A different approach is to use spread spectrum algorithm. Cdma is an example of something that uses spread spectrum that allows you to identify some of these additional delayed portions of the signal, and instead of having them affect your performance, you can either filter them out or actually even use them to improve, to boost your signal. Okay, so those are things that we will talk about briefly, is the use of more advanced communication techniques to deal with some of the problems with respect to the coherence time and delay spread. But with respect to coherence time, it clearly will also have a role in what you can do for a channel. So let's think about that for a little bit. So we talked about these discrete time channel models. That are Markovian. So the simplest possible channel model that's Markovian is a two-state model. Sometimes it goes by the name of a Gilbert-Elliott model. And in this model, there's basically two possible values that the channel can have. It's either 0 or it's 1. And the Markov chain has all of these possible transitions between the states, which are defined by corresponding probabilities. So P00, P01, P10, P11. So what the 0 and 1 represent is something about the channel condition. Okay? So naively, you can think of 0 as bad and 1 as good. To use notation we've already used, we can think of bad being an outage event. Okay? So this is that the SNR is below some threshold that we're calling an outage threshold. And it's good whenever gamma is bigger than, right, or equal to this outage value. So in this two-state Markov chain, it's telling us a lot more than just the probability of outage. So one thing is that if I give you these 4 numbers, you can figure out the probability of outage, because that would be the steady state probability of being in state 0. Right? It will be like long term, how much time do I spend in the 0 state, in the outage state? But these parameters do a little bit more than that. They allow us to control how fast the channel will switch from zeros to ones and back. In other words, we can, by choosing these numbers, not only affect what the outage probability will be, but also affect what the coherence time will be. Right? So let's think about that for a second. First of all, can I choose all four numbers arbitrarily? No. What is the constraint they must satisfy? They have to add up to 1 going out of any given state, right? So first of all, there's already a constraint that P00 plus P01 must equal to 1. Or in other words, P01 must be equal to 1 minus P00. And so these are basically constraints. Similarly, P11 plus P10 must equal to 1. And P, different way of writing that is that P10 equals 1 minus P11. Okay. So if I take any two of these four numbers such that I take one from these and one from these two, then I fully specified this model. Right? So to specify the model, enough to give two numbers. Okay, so I could pick P01 and P10, P00 and P11, or P01 and P11, and so on. Okay. By convention, a lot of the times we find it convenient to just look at P01 and P11. It's just a convenience, right? Because we can always infer the other numbers for each pair from it. So if I give you this pair of numbers, I've fully specified the model. Okay. So intuitively, so let's say we keep all of the states coming out of 0 fixed. Let's say we keep P0 0 fixed, or what is it called, P01 fixed, and vary P11. What happens? What should happen to the coherence time? So let's think about that for a second. Sorry, 10. So I'm keeping these two numbers fixed to some value, and I'm just varying P11. Okay. So as I vary P11, starting from a very low value, starting from very close to 0 to very close to 1. What will happen to the coherence time of this channel that we're describing? When will it increase? Will it decrease? Will it increase and then decrease? What's going to happen? Let's build some intuition about this model. It'll increase, you're saying. So if I increase P11, when it is very low, then if I'm at 1, I rarely come back. Which means that whenever the channel is good, with very high probability, it's going to go bad right away. Okay? So it doesn't stay coherent very long. The good channels go to bad very quickly. Right? Similarly, if I am at state 0, well, if I'm at state 0, varying P11 is not going to change anything. That's governed entirely by P01 and P00, but those I'm keeping constant. But certainly if I'm at state 1, how quickly I can transition to the next state, that's a function directly of P11. So the higher P11 is, the more likely I am to come back to the same state, and intuitively that should improve my coherence time. Likewise, so let's just write that down. So as P11 goes up, you expect T-coherence to go up, right? So likewise, what do you expect would happen with P00? If I fix, let's fix P11, and I increase P00, am I going to increase or decrease the coherence time? Increase. Right? So this model kind of seems to do that. Now, what's a good definition for the coherence time for this model? We don't have to look at a book to figure it out. We can just use our own intuition. Okay? So this is part of something I keep hoping I'll be able to communicate in this class. I don't know how successful we'll get, but I want you to start thinking of mathematics as a creative tool, as something that you can choose, you have a lot of freedom in, right? We often, when we're taking math courses, you're looking at a textbook and there's some equation there, you memorize the equation, then you plug in numbers to it, and then you use it. But I want to kind of free us a little bit from that and realize that mathematics is just a tool. So we get to define whatever we want. So we're going to define for ourselves what coherence time should be. Okay? So we have some intuition. We want, whatever this coherence time is, we're going to define it in such a way that when P11 goes up, we want it to go up. When P00 goes up, we want it to go up. Right? So let's think about this for each of them separately. How might we relate P11 to a certain time element? Is there anything about just being at state 1 and with this probability coming back to state 1 or staying in state 1 or moving to a different state? Is there a time that I can relate to this probabilistic phenomenon? So think of it this way. I'm at state 1. I keep tossing a coin. With probability P11, I stay there. With probability P10, I'm going to transition out. Right? So if I ask you, this notion of coherence time is kind of like how long does it take me to switch? Right? Is there probabilistically something we know we can use to capture that notion of a switch? So I guess I'm trying to say, if we're at state 1, how long will it take to switch? So if I'm at state 1, right, and I keep tossing a coin with probability P11, I don't switch. With probability P10, I switch. How long will it take me to switch? What does this problem remind you? Is the expected value, right, of what? Of the expected value of P10 is just P10. Of a certain random variable with this parameter. What type of random variable? It's like a coin toss, right? If you remember this problem from early on, you are tossing a coin, you're saying how long before you see the first occurrence of, let's say, heads. Right? So what is that random variable called? Binomial, right? So it's basically a binomial random variable with the parameter P10, or 1 minus P11, they're the same thing. And so the expected number of coin tosses before you see the first success, that's the time it'll take you to switch. Okay. So how long will it take you to switch in this case? Anybody remember? So if I have a coin toss and it comes up heads with probability P, how long do I wait before I see the first heads on average? One minus?
P into 1 minus 2.
No, that's the variance, I think. The expected value.
Or n minus 1 into 2.
That's the distribution. That's the PMF. We want the expected value. So what we're looking for is called the expected value of a binomial. And a different way of saying this is sort of expected time to first success with success probability P. Okay. N times the probability of success is the expected number of successes in n trials. So that would be a different... Sorry, this is not a binomial random variable. It's a geometric... Thank you. You did clarify the issue. So n times p is the expected value for a binomial random variable, but the binomial random variable measures the number of successes in n trials. What we're looking for is the time to the first success. That's called a geometric random variable. So for a geometric random variable, if I keep tossing these coins, the time that it takes me to get to the first success is simply 1 over that probability. So if I have, the highest p can be is 1, then I would just, in one turn, get my success. If it is a probability half, like a fair coin, then on average it'll take me 2 tries. Sometimes it'll take me longer, sometimes shorter, but the expected value is 1 over p. This is something you've seen in 503. It might be worthwhile just going back to look at your notes as to why it's 1 over p, but you can derive it a number of different ways, including just from the distribution by computing the expectation over that over the distribution. So 1 over p is the expected time for first success. So if I'm at state 1, the success in this case, or the event I care about is a transition event, that happens with probability p10. So the expected number of time steps for me to go out of 1 to 0 is 1 over p10. Okay. So let's go back to this. So if at in expectation. So, and this is the same as 1 over 1 minus p11 to switch. Okay. Similarly, if we're at state 0, then how long would it take to switch? One over p01. And we're just using p11 and p01 as our parameters, so that's is the expected time to switch. So if we were to think about this, more positively, this is sort of the coherence time for each of those two states. Now, if I want for my channel a single number representing the coherence time, what would be a good number to pick? Should I pick that number? Should I pick this number? Should I pick a different number? How about a combination of the two? Like an average of the two, right? Now, we can average them equally. That would be a reasonable definition. So here's a possible definition. That would say T coherence equals half of, T coherence given that I'm at state 1 plus T coherence if I am at state 0. So this would be one way I could define it. But if you look at it, it seems to be saying that you're just as often at state 1 as you are at state 0. Is that true? It seems to say that we should treat both of these cases equally, like they're both equally likely to happen, that you're switching from a 0 to 1 or from a 1 to a 0. Is that true that they're both equally likely? No. How likely are you to be switching from a 1 to a 0? It's basically in the long run, the steady state probability of being at state 1 and then wanting to switch out of it. Likewise, this should be happening in the long run, the steady state probability of being at 0 times how long does it take you to switch out. So probably a slightly better definition, which gives them the two values the right weight, would be with probability pi 0, where there's the steady state probability of being in state 0, pi 0 times T coherence for 0 plus pi 1 times T coherence for state 1. So this quantity over here is what we're calling T coherence for 1. This is what we're calling T coherence for 0. What are these two numbers, pi 0 and pi 1? So let's go back to our Markov chain. So if you remember from 503, if I give you a Markov chain, you can, there's actually a couple of different ways in which you can compute it. You can actually compute the steady state probability for that chain. And one of the easiest ways to do it is to use something called global balance equations, which basically says that the rate at which you transition from 0 to 1 in the long run must be the same as the rate at which you transition from a 1 to a 0. And along with the underlying rules about how these two are related, the constraints, you can basically derive the steady state probability. And if you did that, you would find, and I'm not going to work out the equations here, but I do recommend working this out. But if you worked it out, you would find that the probability in the long run of being at state 1 is given by P01 over P01 plus P10, and pi 0 is given by P10 over P01 plus P10. Actually, I might as well just write down. So the global balance equation here would have been pi 0 times P01 must equal pi 1 times P10. And you also have the condition that pi 0 plus pi 1 must equal to 1. So if you just work through these two equations, you should find yourself with these values. Okay. So we have these equations. We had the equations back here. So with all of that, we can kind of conclude some definition for coherence time for this model is going to be just pi 0 times 1 over P01 plus pi 1 times 1 over 1 minus P11. And if I put it all together, we get pi 0 itself is P10, which is 1 minus P11. Okay, let me just leave it in this this form. It'll be easier. So it looks kind of complicated. You can simplify all this to be just a function of P01 and P11, because wherever you see P00, it would be 1 minus P01. Wherever you see like P10, that's like a 1 minus P11. So you can simplify this expression a little bit further, but ultimately the point is just if I give you the model, you can compute the coherence time. And in the model, you'll find that both P01 and P11 will have a role in changing the coherence time. So what good is this model? One thing we can do with it is we can capture what we actually observe in the real world. We can see how frequently do you see a good channel going bad, how frequently do you see a bad channel going becoming good, and use them to kind of infer these two numbers. And from those numbers, you can now simulate that environment, right? But besides simulating the environment, you can also do prediction. So you can ask now questions like, if I'm now in a bad state, how long will it take for me to become a good link? Okay. And in one of the assignments, we'll see, using such a model, given this coherence time parameter, what's the best time to retransmit a message? So if I've just sent, I think we talked about it last time, if you send a packet and you get back a response that you didn't, or you didn't get back a response because the packet didn't go through, then that means that you're in a bad state. If you know the model, you've learned the model over time, you've learned that the channel tends to stay bad for this period of time, then that might inform how long you should wait before resending the packet again. In the meantime, if you were to send a packet because you already know from your understanding of the model that the channel is likely to stay bad, you're just wasting the transmissions. You might be wasting power, you might be causing more interference for other nodes. So by basically modeling the temporal dynamics in the link, you can make your links more efficient. Right? So that's an example of how we can use it. Okay. So we'll come back to this model and this particular link adaptation question again. So let's talk about briefly some of the techniques at the physical layer in wireless communications that get used. And one of these techniques is called OFDM, which stands for orthogonal frequency division multiplexing. And one way to think about OFDM is you're taking your available bandwidth, and we're going to split it into a number of what are called subcarriers. So this is the overall, total bandwidth. And we break it up into a number of subcarriers. And each of the subcarriers has its own version, its own stream. And the overall throughput that you're going to get will be the throughput in each of the subcarriers multiplied by the number of subcarriers, right? So total throughput equals throughput per subcarrier times number of subcarriers. But a different way of looking at that is that you wanted to send this throughput, but each of the subcarriers is only sending that total throughput divided by the number of subcarriers. So for example, if I have, 32 subcarriers, and I'm trying to send a total bandwidth of 100 megabits per second, each channel only needs to carry a little bit over 3 megabits per second. Okay. So effectively, each subcarrier stream is a lower rate data stream. And we talked earlier about these channels which have intersymbol interference. If I were to send the whole thing as one high rate stream that occupies a larger bandwidth, what will happen is that those symbols will be in time so close to each other that they will start smearing into each other as the multipath reflected versions of the symbol show up. But by cutting it so that each subcarrier is only carrying a lower rate stream, the symbol duration for each one of those is made larger, and now you get more robustness to the interference from the previous symbol. So just to kind of visualize what's happening, imagine that you're sending your data at a certain symbol rate. So basically this is what we call T symbol. Right, so here's symbol 1, symbol 2, symbol 3, symbol 4. If I have a certain delay spread, okay, let's kind of visualize it as being a certain duration. I don't know, let's say it's about this long. Okay. So what this means is that when I send my first symbol, I'll get the first version of it at some time, but then time shifted by additional time periods, I'm going to get additional reflected versions of that symbol. Okay? And when I get these additional versions of that symbol, some of them are going to smear into the next symbol. So when I actually send this, what I receive looks like I got this, plus I got something where the first symbol is actually smearing into the next symbol, right? And this symbol will arrive but smeared into the next symbol. The third symbol will be smeared into this symbol, and so on. Right? And so because of this period of time where the symbols are interfering with each other, I'll have a tough time decoding each of these symbols. It's as if I'm kind of interfering with myself. Right? So the idea is that if I could stretch my symbols out to be larger, so make the symbol duration larger, cut down the rate of that stream. So maybe my first symbol is only 1/30th that, or let's take in a simple example like this, let's say it's only 1/5 of that. Now my first symbol is, let's just assume this is my second symbol that's coming. Here's my first symbol before that. Now for the same amount of spread, the previous symbol will only interfere with this small portion of the next symbol. Right? So I can basically, by extending the size of the symbol, reduce the interference from the previous symbol. Right? So increasing symbol duration reduces interference. And so in OFDM, what we're doing is that every one of these subcarriers, because their throughput can be small compared to the original throughput that you wanted to transmit at. So if you want to reduce your throughput, you can increase your symbol duration. So each of the subcarriers has a longer symbol duration, and this gives you robustness. And so that's one reason why you'll see that a lot of high-speed wireless links use OFDM. Okay, this is probably their single biggest advantage. Okay. And again, these are techniques that you can spend a lot of detail on in a comm course, but here I just want to give you the idea. Why do we use OFDM? It's because it allows us to take the total bandwidth, split it into a bunch of subcarriers. Each subcarrier can be a lower rate subcarrier, which means the symbol durations are bigger, which means that if you're in an environment where there's a lot of echoes and delay spread, the symbols don't smear into each other, and so the performance is better. That's basically the idea, right? It's just an intuitive story. So I want you to keep that story and not worry about all the mathematical details of how OFDM is implemented, which there is quite a bit of. Similarly, there is a class of techniques known as spread spectrum. And broadly, spread spectrum techniques are divided into frequency hop and direct sequence. Sometimes you'll see these abbreviations used. So, as the name suggests, spread spectrum, the idea is that you're communicating your information by occupying a larger bandwidth. And the hope is that you're doing this to gain some advantage for your system. With frequency hopping, the idea actually goes back a long time to World War II, where it was used as a technique initially developed for anti-jamming. The idea is very simple. You're describing, for example, your communication as happening over a set of frequency channels and over time. So imagine that you split your data across many different frequency channels, and at each time you pick a different channel to occupy. So for example, maybe at this time 1, 2, 3, 4, you're using this frequency. At time 2, you're using this frequency. At time 3, you're using this frequency. At time 4, you're using this frequency. And at some point, the pattern will repeat, but it's kind of saying at these times use these frequencies, and you hop between the frequencies at different times. This scheme, which is actually used in Bluetooth, for example, gives you some robustness to jamming because either whoever is trying to jam your communication needs to occupy all of the channels, which imposes bandwidth costs on that adversary, or they can only jam one channel at a time, but they don't know which channel you're on. So to the extent that you can keep your hopping sequence a secret, or you can vary that over time, or you have a large enough sequence that's only known to the sender and the receiver. Of course, both sender and receiver have to be synchronized to each other. They both need to know now which frequency to jump to, now which frequency to jump to. So that's pre-arranged. Then for the jammer, it becomes really hard to figure out which frequency to jam, because if they jam any one frequency, you'll hop in and out of it very quickly. At most, you lose when things are bad on that frequency. You can also see the advantage of this if you have frequency selective fading. If we have those environments we talked about, we said that if you have a very high delay spread channel, you have a low coherence frequency, that means that different channels have different qualities. By sending your communication at different frequencies at different times, even if some of them are affected, the others are likely not. So you get sort of robustness in the presence of frequency selective fading. You also get robustness to external interference. So nowadays, we're not worried so much about somebody adversarially jamming our communication, but there may just be other devices nearby that are also using the same frequency. So for example, Bluetooth operates in the same frequency as 802.11, same frequency as 15.4 and other devices. So by using many different frequencies, you kind of give yourself some robustness to any one of those channels being really bad. Right? So it gives you some diversity advantage. So this is a form of diversity improvement. Okay. So that's really all frequency hopping spread spectrum does, is that by using different frequencies at different times and following a certain sequence, and correspondingly using a larger portion of the spectrum, you're getting some robustness to interference, robustness to frequency selective environments. Okay. Direct sequence spread spectrum is a little bit more complicated to explain, but not that much more. So the idea is that you have your a spread sequence, a spreading sequence, okay, that changes at a higher rate than the symbols. So let's take a very simple example where you're just communicating a binary stream. You have a bunch of zeros and ones. And originally you wanted to communicate just 0, 1, 1. Let's just take this simple example. Okay, so this is the original symbols. And you have now a spreading sequence we're going to use. And the spreading sequence in this simple example, sometimes it's called a chip sequence, or and let's say the sequence happens to be 0, 1, 1, 0. Okay. And let's do that again. So I'm just giving a very naive example to give us the idea. So what you output is basically some combination of your original symbol and the spreading sequence, and often you can think of it as just an XOR of the two symbols. So what you actually send is this sort of coded sequence, if you will, that is the XOR of both of them. So in this case, you would just send 0, 1, 1, 0, 1, 1, 1, 0, no, 1 again. 0, 1, 1, 0. No, this is also 1. Sorry, this is OR. XOR would be if they're both the same, and it's a 0. Right? So 1, 0, 0, 1. So you're sending this coded sequence. So what you finally send out is sent at, in this example, 4 times the higher rate of the original symbol. And so because it's being sent at a higher rate, it's going to occupy a larger spectrum. The advantage is that these sequences themselves are designed to have certain properties. Right? So they're designed to have certain properties. Such as high autocorrelation, and we'll talk about what these mean briefly, or in the case of Cdma, something we care about is low cross correlation. Other sequences. And sometimes it's the same spreading sequence has both properties, or you have 2 different sequences that you apply to what you're sending out. And then at the receiver, you basically decode using the same sequence as at the transmitter. So now, for example, we got 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1. And now I decode it by applying this 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. So this is what I received. Right? Here's the decoding sequence, which is the same. And if I were to XOR these two, what would I get? So I'd get 0 XORed with 0, 1 and 1, 1 and 1, 1, 0 and 0. Here 1 and 0 give me a 1, 0 and 1 give me a 1, 0 and 1 give me a 1, 1 and a 0 give me a 1. And likewise here it's a 1, 1, 1, 1. Right? And now at the original symbol rate, if I were to view what I receive, it's basically giving me a 0 for this whole period of time, a 1 for this period of time, and a 1 for this period of time. So I can then decode back what I'd originally sent. Right? So why would I bother doing this? Why did I go to all the trouble? If I should have just sent what I had originally had at the sender, everything would have been fine. Right? We've gone to a lot of trouble to encode that sequence in a faster rate, occupying a larger bandwidth, and then decode it back again with the exact same symbol. But it turns out that just doing this alone can give us a lot of interesting properties. So one thing is that the reflected or delayed versions of the signal will, for a properly chosen sequence, with high, oh, it's actually not high, it's, the phrase is peaked autocorrelation property will be filtered out. So the reason for this is that if I send my original signal and encoded by the whatever the chip sequence is, right? And then I decode it with the same chip sequence, I get back my original signal. But if I take the time-shifted version of this, which is there's some time shift being applied to the signal, and I try to decode it with the original chip sequence, what I'll get back will be basically something that's, it would basically be ignored. And so when I'm sending my data through a channel that's introducing delays, what I'm getting at the receiver is both the original sequence plus a bunch of delayed versions of that signal. And if I choose this chip sequence to have the property that these time-shifted versions don't correlate with the original sequence, when I'm decoding them, they basically will get filtered out. They won't show up in the received signal. And so even though they have all of this multipath reflections happening, I'm getting the original symbol plus delayed versions of that symbol. The delayed versions of that symbol don't correlate well with my decoding sequence and essentially get filtered out. Right. So again, this is not the class for us to get very deep into the idea, but the takeaway lesson is that by using carefully designed spread spectrum sequences, these chip sequences, you can essentially filter out delayed versions of the signal and therefore perform really well even in environments with high delay spread. So even if you're not using OFDM, but you're using DSSS, that's one way in which you can improve your robustness to the problem of intersymbol interference. Right? So basically helps with reduce intersymbol interference. The other interesting property is that if two different transmitters are sending their data encoded with different chip sequences, or spreading sequences carefully selected to be orthogonal or have low cross correlation, then at the receiver can filter out the interfering signal. What I mean is, if I imagine I have a system where I have a transmitter A and a receiver A, a transmitter B and a receiver B. So I'm trying to operate both of these links in the same channel, in the same physical region. But this one is encoded using chip sequence, let's call it C1. This one is encoded with C2. So the spread spectrum sequences that we're encoding at the transmitter are different for the two of them. This receiver will try to decode with C1. This one will decode with C2. But because they're in a wireless medium, this signal will also arrive at the receiver. So what the receiver will see will be a combination of the original signal from A as well as B. But the signal from A is encoded with C1. The signal from B is encoded with C2. But it's decoding with C2. If I chose these two sequences, C1 and C2, to be orthogonal to each other, and again, how do you do that? That's outside our scope, but it is possible. And in this case, when the receiver decodes it, it will only filter out the interfering signal and will get all of the signal from its own sender. Okay? And likewise, when transmitter B signals are received at A, it's able to separate them out. Okay? This technique of using spreading sequences to allow multiple links to access the same channel, so using orthogonal sequences to allow multiple links to access the same channel, is known as Cdma. Okay, so I want to make one thing kind of a little bit clear. So spread spectrum is sort of a broader term. It applies to both frequency hopping spread spectrum as well as direct sequence spread spectrum. Okay, this can be used for single links. For example, although we're all starting to replace them now, but probably all of you are old enough to have had a cordless phone at some point in your homes. A cordless phone often uses a direct sequence spread spectrum. It's just a single link. You're not allocating different chip sequences, different phones. If you just have a single base station and a single phone, wherever you go, it's sending the data over a spread spectrum chip. So you could use it for a single link, but you could also use for multiple links. And if it's used for multiple links with orthogonal codes, sequences or codes, then we call it Cdma. Okay? So Cdma is a spread spectrum technique that uses direct sequence spread spectrum, allocates different sequences to different links in such a way that they won't interfere with each other. But even if you're not using it for multiple links, you can still find the direct sequence spread spectrum is useful, because by doing this, it allows you to be robust to delayed versions of that signal, so it helps reduce intersymbol interference. And it is also useful because it may help filter out other interfering communication from other devices. Because when you decode it with your particular chip sequence, if they haven't encoded with that, depending on the choice of the sequence, you'll be able to decode your signal stronger. So it sort of improves robustness to interference as well as frequency selective environments. And this also improves robustness by giving you more frequency diversity. So spread spectrum techniques are broadly used in wireless to give you better performance with respect to these types of issues. So we have a little bit of time. So the other class of techniques I want to talk about, and again, we won't get into very much in detail in this class, is error control coding. Or sometimes referred to as forward error correction. Okay. So the basic idea with forward error correction in digital communications is that you're basically adding redundant bits in order to reduce the error rate. Broadly, forward error correction schemes fall into two categories: block codes and convolutional codes. With block codes, what we do is we take take a block of k bits. Actually, let me just make sure I'm consistent with standard notation here. Block code, coding rate. So k bits of input data and output, right? Okay. So k bits and output n bigger than k bits. And this output, this is called a code word. The idea is that the additional n minus k bits are used to provide robustness to bit errors. So you can think of the most naive form of error control coding would just be repetition coding, right? So the most naive thing to do would be just replicate. So you would just take, let's say I'm trying to send blocks of 3 bits. And it could be any 3 bits that I'm sending. A replication code would simply just send the same bits twice. So I would just send 101, I send 101 again. If I send 111, I send 111 again. Right? It's going to help me with detecting if there is an error, right? But it's actually in this simple example of just replicating it once, several things can go wrong. One thing is, if I do find at the receiver that one of the bits got flipped, let's say what I received was 100101, I actually don't know which of the two events happened. Is it that this 0 was a 1 that flipped into a 0? Or was it this one that used to be a 0 but got flipped into 1? I just know that there's an error in this bit. Okay. And with these 2 bits, because they're in agreement, I might decode them and say, I believe these bits to be correct. There's still a small probability, although it's a lower probability, that both of them got flipped. Maybe both this turned from a 0 to 1 and this turned from a 0 to 1. Right? So it turns out generally the simple replication coding is not very efficient. We've used a lot of bits to add redundancy to our original information, but it's not necessarily bought us a lot. Okay. Having said that, we use replication coding in real systems all the time. The simplest example is backing up your files. Right? what we typically do to avoid failures of all our data is we just keep a copy of it somewhere else. We're just taking all the bits we have. We've created a replica. If something happens to this, we go and grab the replica. We're assuming that failures are unlikely to affect both of those, because in that example, the two are physically separated. Right? But in communication channels, if they're going through the same channel, it turns out to be not a very efficient way of encoding your information. So block codes are, think of them as very carefully designed transformations. There are linear block codes, which are just linear operations you perform on the input code words to generate the output code, input bits to the output code words, and then a corresponding decoding operation that comes back from the received code word to the original bits that tries to minimize the probability that your decoded values are in error. And I won't get very deep into it other than to say that intuitively you can imagine that the more bits you add, the more bits you're willing to add in your encoding, the stronger the property would be. So this ratio k over n is sometimes called the coding rate. And the lower the coding rate, the better the error performance. Why? Because when you reduce k over n, you're basically increasing n minus k, and you're adding more redundant bits, and that's going to improve your performance. So there's a trade-off in using block codes that has to do with basically what is that ratio. So block codes work by taking k bits and just outputting a larger bit as a code word, and you're basically operating on each of these codes independently with each other. So you take this block, encode it, take this block of bits, encode it, take this block of bits, encode it. The challenge with block codes is that they introduce some delay for coding and decoding. You have to wait to fill up a certain block length of bits, run them through the encoder, send it out. At the receiver end, you have to receive that code word, run it through the decoder, and then you got your bits, right? That works well for packetized communications when you have that the block length is the same as the packet length. So you can take the entire packet, encode it into a certain code word of the data, encode it into code word, put that code word in your packet and send it out. Sometimes it can work to your disadvantage. What if your block length is much larger than your packet size? In which case you have to first encode many packets worth of data, get the code words, send the code words out at the receiver, collect all of those packets, then decode them back. So you add some additional delay for having to wait to gather a bunch of packets before you can decode, right? So depending on the particular scheme that's used, what the length of the code is, what the length of your packet is, and so on, it may add some additional delay. So an alternative to block codes, also for performance reasons, that's often used is known as convolutional codes. And it's still true that they're still described by a coding rate that's like k over n, in that every k bits of the original data generates n bits of encoded data at the output, but the encoding is continuous. Or stream-based. And the way it typically implemented using shift registers and logic operations over shift registers. Just to give you an idea, maybe what you end up doing is you have, here's a simple example, there's sort of 3 shift registers. So your input sequence at any given time might have some set of zeros and ones as they stream in, and then there's some digital logic operation defined on all of these, some Boolean operations that are implementing the convolutional encoder. And it has a certain number of outputs. So in this example, maybe for every 3 bits, you output 4 bits. And so here's your output 1, output 2, output 3, output 4. But it's a stream processor in the sense that these are the bits that it outputs at the current moment. Then as you shift, it's going to output a different set of bits and so on.
Excuse me, Professor, is your 5-minute warning?
Okay. And so the point is that which 3 bits you're operating on will be, the 3 consecutive bits, and which 3 bits they are just keep shifting over time, right? And so it's not that we took these 3 bits, first encoded them, then took another 3 bits, and then encoded them, but rather as they keep shifting through, we keep running the encoder, and it keeps spitting out bits on the output. Actually, maybe this example is too extreme. Let's just say it has 2 outputs. Then every time a new bit gets added in, you're outputting 2 bits. So this would be a rate half encoder. Example here. So every time you get these set of bits, it's outputting 2. The size of this memory has sometimes properties associated with how good the encoding is, how much robustness you can get. Intuitively, the more complex the encoder, the more robustness it can provide, but then you're paying for it by increasing the complexity at both the encoder and the receiver ends. On the decoder end, so for block codes, it's very simple. It's basically just a lookup table, right? You get this particular code word, you should output this bit, or some other decoding algorithm. On the in the case of convolutional codes, there are a number of techniques that have been used for decoding convolutional codes. One that was very popular and has been used for many years can use algorithms such as the Viterbi algorithm. So the big contribution of Andy Viterbi, who lent his name to our school, was developing an algorithm to decode convolutionally encoded bits. Okay, and this algorithm and implementations of this algorithm are used in virtually every mobile phone, even to now, that uses convolutional codes. There are more advanced versions of convolutional encoding and decoding that go by names such as turbo coding, if you've heard of that. There are also these LDPC codes, etc. Okay, so there's a whole arsenal of algorithms for encoding and decoding that have been developed that are basically variations of convolutional coding that are extremely efficient at reducing the error rate. And in particular, all the way from the 60s and the 70s, when people were starting to develop wireless communication systems, one of the big open problems in communication theory and communication systems was to develop codes that approach something called the Shannon limit. For a given SNR, how low can you drive the bit error rate, right? And so the Shannon limit kind of describes how low the bit error rate could possibly go. And in the 90s, turbo codes and LDPC codes were first shown to achieve the Shannon limit arbitrarily closely. So today, in terms of error control coding, we've basically completely solved the problem. We know how to encode our information to drive the error rates as low as possible. Right? But implementing these codes does require computational complexity, so they're not used in every piece of software or hardware that we use for radio communications. But for high-end things like cell phones and other high data rate communication systems, we routinely use these very advanced coding techniques that basically reduce the probability of error to as low as it can be by carefully encoding the bit streams. So, when you read a particular wireless standard, you'll hear about all of these different terms like OFDM, spread spectrum, frequency hopping, Cdma, convolutional codes, turbo codes. They're just referring to different techniques that are implemented at the physical layer to improve performance. So I think there's one more of these techniques I'll touch on next class, which is MIMO. But other than that, I think, and also here you've seen we haven't gotten very deep into how each of these work. For example, for error control coding, there's a whole course that we used to offer at USC in our EE department that's just about error control coding, right? And spread spectrum was a whole course in itself. So there's a lot of depth to each of these subjects, but here we're just kind of giving you the idea of what they are. Our focus in this class is going to be at the higher layers. But again, if somebody says turbo code or Cdma, you should have an idea of why that shows up in a wireless physical layer. So we'll stop here. There will be a homework assignment I'll post hopefully by tomorrow that will be due the next Friday, and you have one assignment that's due this Friday. All right, we'll stop here for today. Thank you.
This has been EE 597 with Professor Krishnamachari on Wednesday, May 25th, 2016.